Welcome back to Math 104. What is the probability that a randomly selected patient receives the actual drug but does not get better? Based on the wording, we can see that this is an unconditional probability. We are talking about a randomly selected patient. That means selected from the entire group of patients, not from some narrower group of patients. So what is the probability that a randomly selected patient, selected from the entire group, receives the actual drug but does not get better? Logically speaking, but means the same thing as and. We could just as easily say, receives the actual drug and does not get better. We are talking about this event, the event A intersect B complement, took the actual drug and did not get better. That probability equals the product of this 0.7 and that 0.2, so 0.7 times 0.2 equals 0.14. You could also say that 14% of all the patients have taken the actual drug and not gotten better from it. Our next question is, what percentage of patients get better? Equivalently, what is the probability that a randomly selected patient gets better? First, let's notice that this is an unconditional probability. We're asking about a randomly selected patient. Just randomly selected patient. That means randomly selected from the entire group of patients. That makes our probability that we're trying to find an unconditional probability. Now, how do we find it? The event here is a little bit more complicated, so we need to think, what's involved in the patient getting better? What are all the ways that that could happen? It could happen by getting to this location in the tree, by taking the actual drug and then getting better, or by not taking the actual drug but getting better anyway, so a patient could get better by arriving at either of these two locations in the tree. This means that B itself can be thought of as A intersect B, let me put that in parentheses, union A complement intersect B. Any randomly selected patient inside this event is also in B. It's also true that any randomly selected patient who is in this group is in the event B. So every outcome in A intersect B or A complement intersect B is in B. Now notice that A intersect B and A complement intersect B are mutually exclusive of one another. It's impossible for the same person to take the actual drug and get better, and also take the placebo and get better. A patient could be in only one of these, but not both. That means that when we compute the probability of B, it equals the probability of A intersect B plus the probability of A complement intersect B. Union turns into plus. We don't need to subtract off the intersection between these two events because there is none. We've seen this before earlier in the course. That's the great thing about working with unions of events that are themselves mutually exclusive. This equals 0.7 times 0.8. We've seen that before, 0.7 times 0.8, plus this probability of not A followed by B, that's 0.3 times 0.4, so 0.3 times 0.4. When we compute, we get 0.56 plus 0.12, which equals 0.68. This is the probability that a patient gets better. This is sometimes called the total probability of B, the overall probability of B. In percentage terms, we can say that 68% of all the patients get better. That last question was a little bit more involved. There were a number of different decimals we had to compute with. It gets harder to hold on to our intuition. To make this as intuitive as possible, the information in this problem can be interpreted in terms of an ideal data set of 100 patients, and that can be put into a frequency table. Out of a perfectly representative group of 100 patients, how many took the actual drug and got better? We've seen that the probability of taking the actual drug and getting better equals 0.7 times 0.8, which equals 0.56. So 0.56 times 100 equals 56. Among the 100 patients, there are 56 who took the actual drug and got better. By the same thinking, there are 0.7 times 0.2, which is 14% of 100. That's 14 people who took the actual drug but do not get better. How about those who took the placebo and get better? We computed that probability to be 0.3 times 0.4, which equals 0.12, or 12%. 12% of 100 equals 12. And finally, 0.3 times 0.6 equals 0.18. 18% of 100, that's 18 actual people, took the placebo and did not get better. We find that the total who took the actual drug is 70 people. That agrees with the given information that 70% of all the patients took the actual drug. Similarly, 30 received the placebo. The total number who get better equals 68, and the total who do not get better equals 32. Notice how concrete this makes the solution to the previous question. We asked, what is the probability that a randomly selected patient gets better? We did some computing to find that that equaled 0.68, but look how concrete it is now. Out of 100 patients, 56 took the drug and got better, another 12 took the placebo and got better. That's a total of 68 who got better. Let's use this frequency table for an ideal data set to compute some more probabilities. What is the probability that a patient whose condition improves took the actual drug? Condition improves is another way of saying gets better. Let's first sort out whether this is a conditional or unconditional probability. It is conditional. How can we tell? We can ask whether we are randomly selecting a patient from all the patients, from all 100 of them, or whether we are zooming in on some smaller group. In fact, we are zooming in on some smaller group. We are looking at those whose condition improves. We are restricting our attention to these 68 people, and if we select just from those 68 people, we ask, what is the probability that someone who gets better took the actual drug? Notice that this is probability of A given B. It equals 56 over 68. Out of these 68 people we're focusing on, 56 of them took the actual drug. This equals approximately 0.8235. This means that of those who get better, the overwhelming majority of them did take the actual drug. This conditional probability is conditioning in the other direction from the information that we were originally given. The original information told us, for example, about the probability of B given A. The original information told us, given that you took the actual drug, what's the probability of getting better? This is now conditioning in the opposite direction. Given that you get better, what's the probability that you took the actual drug? Before going on to the next video, answer the following question. What is the probability that a patient whose condition does not improve took the actual drug? Is this a conditional or unconditional probability?